In this program, we are implementing a fan control using a PI regulator. The program name is Fan Control with PI. Let's start with the variable declaration section. First, we declare PI control as a simple PI reg function block. This is the PI controller instance that will calculate our control output. Next, we declare HND on-off status as a Boolean variable. This variable can be used to represent a hand or on-off status from a system. Then we define manual value of type real, initialized to 70.0. This represents a manual speed value, for example 70%, in case we want manual operation. Control output is a real variable that will store the raw output coming from the PI controller. Limited output is another real variable used after applying minimum and maximum limits. Then we define min speed real and max speed real. These variables are needed to convert integer limits into real format because the PI output works with real values. Now, let's move to the main control logic. First, we check if the PI controller is enabled. If PI control.zenable is false, we immediately set the output to 0.0. That means the fan will stop completely. This ensures safe behavior when control is disabled. If the controller is enabled, we then check whether auto mode is active. If HM auto mode is true, we execute the PI controller. We configure the PI block with the required parameters. Zenable equals true activates the controller. X direction equals false defines the control direction. Xreg type equals true selects PI regulation mode. Our set point equals 22.0 defines the desired temperature set point. Our value equals temperature PV is the measured temperature input. U integral time equals 120 defines the integral time constant, meaning the integral action reacts gradually. After the calculation, the PI block generates an output stored in control output. At this stage of the development, we later realized that we also needed additional variables to complete the control logic properly. So we added temperature PV of type real. This variable represents the process value. In our case, the measured temperature that will be used as input to the PI controller. We also added fan speed of type real. This variable represents the final output that will be sent to the fan or inverter. Additionally, we introduced min speed and max speed as unsigned integers. They are initialized to 0 and 100%. These parameters were added later to allow speed limitation and make the system more flexible and safe. They define the allowed operating range of the fan. Next, we apply speed limits. Since min speed and max speed are UINT values, we convert them into real using toReal. This ensures data type compatibility. Then we use the limit function. This guarantees that the control output remains between the minimum and maximum allowed speeds. If the calculated output is lower than the minimum speed, it will be forced to the minimum. If it exceeds the maximum, it will be limited to the maximum. Finally, we assign control output to fan speed. This is the final value that controls the fan. In summary, this program implements a PI-based temperature control for a fan. During development, we improve the program by adding process value input and configurable speed limits. This makes the system safer, more flexible, and suitable for HVAC or refrigeration applications. And this completes the explanation of the fan control with PI program. Now, let's move to the simulation to better understand how the program works. First, we connect the virtual variables to the physical ones, and then we start the simulation environment. Once the simulation is running, we activate the monitoring process. This allows us to observe the variables in real time. We can see how the values change during execution. By doing this, we clearly understand how the control logic responds. This step helps us verify that the program is working correctly.